All right, welcome. We were talking about hypothesis testing the last video. So we're continuing on section 4.1 in the textbook. So we're looking at two competing hypotheses in order to test some claim. The null hypothesis is the claim that there's no effect or difference, and the alternative hypothesis is the claim for which we seek evidence. All right, so notationally, we're going to do an H subscript 0 or H naught to denote the null hypothesis, and an H subscript A to denote the alternative hypothesis. Alternatively, H subscript 1 is sometimes used for alternative hypothesis, but our book focuses mostly on the H subscript A, so I'll try to do that also for our class. And note, these are both claims about a population. So these are going to involve population parameters, mu for mean, p for proportion, rho for correlation. The alternative hypothesis is established by observing evidence that contradicts the null hypothesis and supports the alternative. So what this is saying is the null and the alternative should oppose each other, but the data, if you have data, the data should support the alternative hypothesis. Now, it doesn't always occur that way, which we'll talk about the next couple of weeks in this class. But generally, we want the data, the evidence, the sample data should support the alternative hypothesis. Okay, let's go back to the ESP example. So we're going to assume ESP does not exist. We'll talk about why in a second. So this is my null hypothesis. And then you have to gather evidence to support that ESP does exist. If you run this test with the 5 playing cards and have someone guess them, with telepathic information, you want to know if the person guesses at a higher rate than 1 out of 5, and then see if that supports the alternative hypothesis. So again, the null is no effect or no difference. And to translate this into parameters, we're looking at p. So the null hypothesis is that p is 1/5. So people are just guessing completely at random if they don't have ESP. And the alternative is that P is greater than 1/5. If someone has ESP, then they should be getting more than 20% of the cards guessed correctly. So again, the null hypothesis is the statement that there's no effect or no difference. The alternative is the claim we seek evidence for, and that evidence comes from sample data. Okay, hypothesis helpful hints. One thing, hypotheses are always about population parameters, not sample statistics. So hypotheses should always involve population parameters. The null hypothesis always contains equality. So there should be a statement of equality or an equal sign. And the alternative hypothesis always contains an inequality, less than, greater than, not equal to. Now, when we get to chi-squared and ANOVA, these are at the very last 2-3 weeks of the semester, the alternative hypothesis gets a little bit more complicated. But basically for chapters 4, 5, 6, 7, and 8, this statement holds. The alternative hypothesis should always have a less than, greater than, or not equal sign, depending on the scenario. So that type of inequality right here completely depends on the problem. So one way to think about this is if you have a hypothesis test, all possibilities, then the null hypothesis is a very specific statement. So this is, equal something, that P has to actually equal 1/5. The alternative hypothesis, going back to the ESP, is P is greater than 1/5, so there's a lot more possibilities in the alternative hypothesis. So this is one way to think about the evidence should always support the alternative. The question is, does it support it enough? And does it support enough to reject the null hypothesis? And we'll talk about that in the next couple of sections. So here's an XKCD comment. I still can't believe schools are still teaching kids about null hypothesis. I remember reading a big study that conclusively disproved it years ago. There's definitely better XKCD comics, but the kind of joke, the punchline in this is a null hypothesis or hypothesis test doesn't exactly disprove something. Remember, we're gathering evidence for or against some claim. So it's more of evidence for, evidence against, not really prove or disprove. All right, let's look at one more example. Sleep versus caffeine. So this is a study done in 2008 comparing the benefits of caffeine, naps, and placebo on verbal, motor, and perception memory from a research journal. So students were given work to memorize, then randomly assigned to either take a short nap or hour-and-a-half nap, a caffeine pill, or a placebo. For this example, we're going to ignore the placebo effect. So think of these two treatments. Either students took a nap or a caffeine pill. 2.5 hours later, they were tested on their recallability on the words they were asked to memorize. So just note the explanatory variable in this is the sleep or caffeine. So the variable is those two options. Did the student, were in the group to sleep, or were they put in the group to take a caffeine pill? Excuse me. The response variable is the number of words recalled. So the question we want to know is sleep or caffeine better for memory, at least in this small experiment about memorizing words. So what is the parameter of interest in the sleep versus caffeine experiment? Is it proportion, difference in proportion, mean, difference in means, or correlation? Well, for this particular test, they're looking at a difference in means. Why is this? The response variable is the number of words recalled. It is quantitative, and an explanatory variable, sleep or caffeine, is categorical. So we're interested in the difference of means between the number of words recalled. So we want to think about the average number of words recalled by the group that slept versus the average number of words recalled by the group that were given a caffeine pill. So we're going to let mu sub s be the number of words recalled after sleeping, the group that slept, and mu sub c is the mean number of words recalled by those that took a caffeine pill. So remember, we're using a population notation here because the hypotheses, null and alternative, involve population parameters. And we want to know, is there a difference in average word recall between the sleep and caffeine? So which of these 5 options would be the null and alternative hypothesis? Well, before I click on the answer, 2 of these we could eliminate right away. It can't be A and it cannot be C. And that's because both of these, the null hypothesis, is not a statement of equality. In A, we're given a not equals, and C, we're given a not equals. So it can't be these 2. So we can eliminate A and B right away. It could be B, D, and E, just looking at the null hypothesis. But if we look at the alternative hypothesis, we want to know, is there a difference in the average word recalled? Or not. The wording doesn't state whether you're going to recall more words for sleeping or having caffeine. So because of the wording of the statement, the correct alternative hypothesis is the not equals. So the null is that we assume the average number of words recalled by these 2 groups, the sleep group versus the caffeine group, is the same. The alternative is that they're different. So again, the null hypothesis is no difference. The alternative hypothesis is that there is a difference. So before we go on, I want to point out D and E could be appropriate a hypothesis if you just change the wording. For example, part D, if you said, is it possible that sleep is better for memory than caffeine, then you would choose D to be your hypothesis. Or if your claim was that caffeine helped memory more than sleep, then you would choose part E. But A and C definitely cannot be correct hypothesis no matter what, because the null is incorrect. All right, so looking at these statements, right here we've got one set of hypotheses, null and alternative, that the 2 means are equal, and the alternative is that 2 means are different. Notice the second set is actually the same as the first, just written in a slightly different way. If you subtract mu1 or mu2 from both sides, you get the second statement. So the following 2 sets of hypotheses are equivalent and can be used interchangeably. So basically, there's nothing wrong with either of these two forms. They mean the exact same thing.